further ado, please welcome Dr. Thank you.
Okay, thanks everybody. So thanks for inviting me for this talk, and thanks for allowing me to do this from Berlin. I'm going to tell you about a line of work that has been going on for some 20 years in sentence processing. We have been developing a computational model of sentence processing that was originally started by Rick Lewis, who I think is sitting in the room, if I'm not mistaken. Is that true? Yes, hi, Rick. Yeah, so he was the one who initiated this line of work more than 20 years ago at Ohio State. I was his PhD student, and since then we have been pursuing many of the ideas that he developed through my students and my postdocs. So some of the lead developers in my group are, you can see them here, and also on this slide. So these are the main people who've contributed to the empirical and modeling work that I'm going to report. And I guess I should also mention that all the papers that I will mention are available from my homepage, and you can also download all the source code and the data that go with each of these papers. And if at the end of this talk you're interested in playing with the model, the latest version of this model is available on GitHub at that link that you can see. And all these links are on my homepage anyway, so you can always go and look at those later on. So I'm going to start by talking about the background ideas that led to this model of sentence processing. The main paper that describes the model is the Lewis and Vasisht paper in Cognitive Science in 2005. And then in 2019, we published an extension of this model in the same journal. So these are the two papers that spell out a lot of the technical details of this line of work. Now, the model that Rick developed back in the late 1990s and early 2000s was inspired by a cognitive architecture called ACT-R. So I'm not sure how familiar everybody is with this architecture, but it's basically a programming environment where you can model a lot of cognitive behavior. For example, experimental tasks that we do in linguistics and in psychology. Now, one of the interesting assumptions inside ACT-R is this idea of a fan effect. So the idea is the following. If I ask you to identify the blue square on the screen that you're seeing right now, you're going to use something that the ACT-R framework calls retrieval cues to look for something that is blue and is a square. And so one assumption in ACT-R is that if there are multiple items in your search space that have the same feature, in this case blue, you will have more difficulty identifying the target item, in this case the blue square. Right? So this is called the fan effect, and you can imagine why, because of this fanning out of the possibilities. If you have multiple candidates matching a particular retrieval cue, you have more difficulty identifying the target, and this takes more processing time. Right? So that's the basic assumption there. Now, this assumption comes from research in cognitive psychology, people memorizing, lists of words or trying to identify images on the screen and stuff like that. But this fan effect also has applications in language processing. So an example is a sentence like this. What you're seeing here is in sentence 1A, what we have is a verb, complaining, that has resident as its subject. So here's resident, here's complaining. And now, in order to understand who was doing the complaining, you have to build this dependency between resident and complaining. And in this particular sentence, something very similar to this fan effect occurs. And what occurs is that you're looking for an animate subject at this point when you're processing the verb, and there are two animate subjects in memory. So this results in an increased difficulty in distinguishing between the correct subject and the distractor noun, which is neighbor here. So if you have a baseline condition like 1B, where instead of neighbor, we have warehouse, then the expectation is that you would have less difficulty in processing complaining in 1B versus 1A. So schematically, you can imagine a situation like this. at the verb, you're trying to retrieve something, retrieve a noun that is animate and subject. And in the first condition, 1A, where you have resident and neighbor, one of the features matches both of the nouns. So the animacy feature matches both of the nouns. So this is what causes the fan effect. And the other feature, subject, matches the subject perfectly, right? So this is the kind of situation that leads to increased processing difficulty in at the verb in 1A versus the baseline condition 1B. So that's basically one interesting application of this fan effect in ACT-R in online sentence processing. So that's one key prediction of the Lewis-Vasish model, which is that if you have a fan situation, you will have increased processing difficulty, typically at a verb. Now, the other class of predictions that the Lewis-Vasish model makes is what I'm going to call facilitatory interference. And the example I'm going to use is the following. In 2A, if you look at the sentence 2A, you should be able to figure out that this sentence is ungrammatical. It may not actually feel that ungrammatical, so I'll read it out for you. The bodybuilder who met the trainers were very impressed by the facilities. It doesn't seem so bad, but it is ungrammatical because the subject is singular and the auxiliary verb is plural. There has to be subject-verb agreement, and that's not happening. And so the interesting thing here is that sentence 2A feels a lot better than sentence 2B, which is equally ungrammatical because it has a singular noun subject and a plural auxiliary. But oops, the big difference is that the noun before the auxiliary is singular here. And this, if I read this out, this will feel really bad. The bodybuilder who met the trainer were very impressed by the facilities. So even without doing an experiment, you can feel the difference. And in fact, I'm sure that many of you produce these kinds of sentences 2A in real life. I produce these almost every day. Even when I'm trying to write carefully, I will make this mistake and produce a sentence where I have an incorrect agreement with a distractor noun. So the interesting empirical observation here is that in reading studies, we find faster reading times at this auxiliary in 2A versus 2B. And the interesting question is why? And the Lewis-Vasish model has an explanation for that, right? So the situation that we have in these sentences is the following. In the case where you've got this illusory sentence that seems okay, you've got trainers and were, what's happening is that the auxiliary verb is looking for a noun that is plural marked and a subject. And what happens is that one of the features matches the distractor noun and the other feature matches the subject. So there's a partial match with each of those two nouns. And what's interesting about the ACT-R framework is that in this kind of partial match situation, the architecture assumes that two processes are triggered at the same time. There's a race that begins to try to complete this dependency and to complete this dependency. And which dependency completes first is non-deterministic. So from trial to trial, you will have one process finishing first and sometimes another process finishing first. And interestingly, this is what results in the empirical observation of faster reading times here than here. So how does that happen? Well, there's a famous result in psychology that is called the race process, not a result, but it's an observation that if you have two processes, A and B, that have a certain distribution of finishing times, right? So this is the finishing time distribution of process A, the finishing time distribution of process B. If one of these two processes finishes first and we plot the distribution of the winner's distribution, distribution of finishing times, the mean of the winner's finishing times will be faster than the mean of either of the two processes. That's how the facilitation happens in the ACT-R architecture. It's a race process that happens, right? So we've got this process A that has a certain finishing time, and this process B, which has a certain finishing time, and sometimes process A will finish first, sometimes process B will finish first, and whichever process finishes first is the finishing time in that trial. And so as a consequence, if you plot the distribution of the winning finishing time, you will see that the mean is shorter in the winner distribution than in either of the other process distributions finishing times. So that's the explanation from the ACT-R architecture for the empirical observation of this faster reading time at WER in 2A versus 2B. Okay? So that's basically the theory, right? So what I'm showing you here now are quantitative predictions from the Lewis-Vassich model. And so what I've done here is that for the fan effect that I explained to you earlier, I generated distribution of processing times in the fan effect condition versus the baseline condition. So I'm taking the difference between the two conditions. So this is the difference in the retrieval times between the two types of sentences that I showed you earlier. And you can see that generally the average fan effect time is positive, right? So you have increased processing difficulty in the case where you have a fan situation, right? So that's the prediction from the model. The other type of process that I just explained was the race process, and here I'm showing you the quantitative predictions from the Lewis-Vassich model. So what I've done here is the model itself has lots and lots of parameters. So what I've done is I'm holding all the parameters constant. I'm only allowing noise to vary, right? So what this is doing is it's creating some non-determinism in the finishing times, and I'm also varying the latency, the amount of time it takes for the system to complete a retrieval. There's a parameter for that, so I'm using a prior distribution on that parameter as well. But the important thing is that I'm holding all the parameters in the model constant to the values that were there in the original 2005 paper. Right? So this is a prediction of the model before any data are actually seen. Right? So now the interesting question is there any evidence at all for this inhibitory and facilitatory interference? Right? So there's a lot of evidence for inhibitory interference in psychology, in list memorization tasks, and all these kinds of tasks that don't involve linguistic processing, right? So pure cognitive psychology experiments. There's also a lot of evidence for facilitatory interference. But the question is, do we see inhibitory and facilitatory interference in sentence processing as predicted by the Lewis and Vassich model? So here's what the evidence looks like. So what I'm showing you here is 12 experiments results from the work of Julie Van Dyke, who was also Rick Lewis's student. So Julie and I were students around the same time of Rick Lewis when he was at Ohio State. So Julie, over the last 20 years, has been assiduously pursuing this question of the evidence for inhibitory interference, and she has published a lot of papers showing what the evidence looks like. And so what I'm showing you here is that from 12 studies that she had done, we extracted the mean interference effect. So this is the fan effect in sentence processing, right? So each of these means, these dots are the means, and these are 95% confidence intervals from which we extracted from the papers that she had published. We don't have her original data. We only have the summaries from the paper. So we extracted the summaries. And this gray bar that you're seeing, this is an estimate of the overall effect across the 12 studies, right? So this is a meta-analysis estimate. This is what we have learned from these 12 studies about the range of the fan effect in the sentence processing manipulations that Julie carried out. And these were, things like the examples I showed you earlier at the beginning of this talk. This kind of example, these sentences are from Julie's experiments, right? So difference in reading time between complaining here, and those are those dots that I'm showing you, right? And so the good news is that if you put the 12 studies together, you see some evidence for an interference effect. So the average is about 25 milliseconds, you can see, and the 95% confidence interval is about, I don't know, maybe 0 to 25 milliseconds. Oh, sorry, the mean is something like 12.5 milliseconds, right? So that's the meta-analysis estimate of the inhibitory interference effect from the studies from Julie Van Dyke. Now, we were very interested in trying to run a high-power replication of one of our studies. So right now we're in the process of replicating several of our experiments, but I'm going to tell you about a replication attempt to reproduce this estimate with a large sample study. So her experiments often had smaller sample sizes, like 30 or 40 subjects. That's a typical sample size in psycholinguistics in reading studies, right? So what we did was we ran something like, in English, we ran 80 subjects in UMass with the help of Brian Dillon. And so we tried to replicate this 2006 design from Julie Van Dyke's paper. So the design is as follows. There are 4 conditions in her experiment. And in the first 2 conditions, subjects are required to memorize 3 words. So the words are, in this example, table, sink, and truck. So sink is the object sink. Okay, so table, sink, and truck. So they memorize these nouns. And then they have to read a target sentence. And in the target sentence, there's a subject noun, boat, and then there's a verb that comes up. Okay, so in the first sentence, what you see is that there's a subject is the boat and the verb is sailed. And of all the items that the subject is holding in memory, the participant is holding these 3 items in memory. They're processing this subject boat and they reach the verb sailed. They have to access the subject of the sentence, which is boat. They are not going to experience any difficulty in identifying boat because table, sink, and truck are not saleable objects. So they don't actually lead to the fan effect that I was talking about earlier. So the comparison condition that she had was this one here. So the second one here. What she's got here is that you've got the same 3 nouns that you memorize. You've got boat as the subject, but instead of sailed, you have fixed as the verb. And so when you read the verb fixed, you have 4 candidate items that can be fixed. So this is the situation where you should experience the fan effect and you should experience longer processing time at fixed versus sailed. That was the prediction that Julie Van Dyke made in her 2006 paper. And so in order to compare these 2 reading times, fixed versus sailed, she also had to have 2 baseline conditions where subjects did not have to memorize anything, right? You need that because you can't compare the reading times of sailed versus fixed because these are different words. So what you really need is baselines for each of these 2 conditions. And that's why she had these 2. Conditions 3 and 4 with no memory load. And so the predictions that the experiment makes now is longer reading times at fixed versus sailed in 2 versus 1, but no difference between fixed and sailed in the no load conditions, right? So basically, the experiment predicts an interaction between the memory load condition and the interference condition, whether you have sailed or fixed. Okay, so there was an interaction that was predicted. So this was the design that we tried to replicate in English. And one of my PhD students is working on this right now. She's finished the English experiment. So I'm going to tell you the results of this English experiment. What my student, Daniela Madsen, did is that she also modulated, or she also added a task manipulation. So the same 80 subjects were asked to do the same experiment with different items. But in the first trial, they were asked to read the sentences and answer very simple questions about the sentence. A simple question would be something like, was the word boat mentioned in the sentence? They don't have to do any deep processing to answer that question, right? So that's what it means to have a simple question. And the same subjects were then brought back several weeks later and shown new items with the same design. And these subjects then had to answer pretty detailed questions about the sentence that they had read. So for example, for the target sentences I'm showing you here, subjects could be asked, what was it that was sailed? Right? So now they have to connect the boat and sailed together in order to answer the question correctly. Right? So they were complex and simple questions, so deep and shallow questions, and that was the task manipulation that we did. And another thing that Daniela, my student, did is that she replicated the entire experiment in German and in Russian. The reason we did that was that we wanted to know if the inhibitory interference effect, the fan effect that Julie found in English, would be reproducible in languages like German and Russian, which have very rich case marking. So these languages have very rich information on each word. And so it is possible that the interference the effect doesn't even show up in these languages, right? So nobody has ever tested that. So that's why we ran a parallel experiment in German and in Russian. Okay, so that's a very long introduction to the Van Dyke and McElry design. So we ran the experiment, and to our great disappointment, when the subjects were actually shown complex sentences, this was an eye tracking study, by the way. So this is first pass reading times, regression pass durations, and total reading times. So when the subjects were exposed to complex questions, they don't show any indication of an interference effect. So you're seeing that the interaction between load and interference, that's the interesting thing here. We don't see any indication of any interaction here. Now, only when the subjects were shown the simple question, so in the simple question answering task, we see some indication of the expected fan effect. So this is the interaction between load and interference, and we see that in a very early measure of processing. This is first pass reading time. So this was the only effect that we found in the English study. And this was a big surprise to us. This has some very interesting implications because if you think about it, if subjects are only showing interference effects in the simple conditions, when they're asked simple questions, what that might mean is that they're processing the sentences very superficially. They're not doing any deep sentence processing anymore. And so you might be seeing the effect of very shallow or what people call good enough processing in this case, right? So the interference effect might show up when people don't engage in deep processing. This is just pure speculation on my part. But what I'm saying here is that we did find an effect in first pass reading time, the expected effect, but only in one of the two manipulations. Now, more surprisingly, we have no evidence at all for inhibitory interference effects in German and in Russian. Right. So right now we're in the process of replicating some of the other experiments that Julie had done, and so by next year I'll be able to report what happens there. Right. Danny is actually in UMass right now running these experiments. Okay, so now I want to show you the bigger picture about inhibitory interference in the literature. So what I'm showing you here is the result of a meta-analysis that we did some years ago, looking at all the reading studies ever published on inhibitory interference effects. Okay, so you don't need to be able to see the names of these papers here. I've just listed them here. But what's important to see here is that the triangles are representing the supposed inhibitory interference effect. Right? So all of these are what we would expect to see given the theory, given the fan effect theory, but we don't expect to see so many null results, and we don't expect to see facilitatory interference effects in this case. So all these are very surprising to us, right? So one thing to notice here is that these estimates, so I've sorted these means, by magnitude. That's why you're seeing them in this neat arrangement here. But what this neat arrangement shows is that these estimates are kind of oscillating around 0 milliseconds. Right, so here's the 0 millisecond line, and you can see the oscillation of the effects around 0 milliseconds. And this is actually a very interesting phenomenon, which I will unpack for you in a moment. Now, but before I unpack that, I want to also tell you what the evidence is for facilitatory interference effects. So that's the race process that I had mentioned earlier. Okay, so what I'm showing you here is also data from the meta-analysis that we had done in 2017. But what I'm showing you here is the estimates from 12 studies. So these are the circles that you're seeing here. The first 10 studies are from other people's published work, and these gray bands this gray band that you're seeing is the meta-analysis estimate based on these 10 studies that I have here. Okay, so clearly, if you look at the gray band, there seems to be evidence for a facilitatory interference effect from the published data. What I'm showing you here in this 11th data set here was a replication attempt that we published recently of this big effect of facilitatory interference that was published. This replication attempt that we ran had many more subjects than the original one here. So the original experiment had 40 subjects. Our experiment has 181 subjects. It took us 4 years to run this experiment on an eye tracker. But we were patient and we waited till we got the data. And so one interesting thing to notice is that if you look at the model predictions, this is the Lewis-Fasich model prediction. That's this part here. You see the model prediction here. The large sample study estimate, the mean of that estimate lands within the predicted range, and there's a reasonable overlap, with the confidence interval from the large sample study. The low sample study that you're seeing here, the original study that we replicated, it has a very large confidence interval, so it's a very high uncertainty, and the estimate of the mean is very large as well. You can see how big it is compared to our large sample replication attempt. Okay? So what's going on here? If we now look at the totality of the evidence on facilitatory interference effects, it's not just these 10 studies, but there are many more studies. These are all the published reading studies on facilitatory interference effects. Again, we see that bizarre fluctuation around 0, right? So here's the 0 millisecond line. All these are the effects that the race process would predict. And there's again these unexpected positive sign effects, right? So there's something very interesting going on with all these published studies. They will find all the entire range of possible effects that you can possibly find if you put the data together, right? Everything that is possible shows up in some study or another. Okay? But theory predicts negative effects here. And in the inhibitory interference data, theory predicts only these positive effects here, right? So what's happening here is something that has been noticed in the statistical literature for a long time. It is a property of these kinds of repeated experiments that if you have low statistical power, you're going to end up in a very awkward situation, which is that if you get a significant effect, the significant effect will be a huge overestimate or will have the wrong sign. Okay, I'm going to demonstrate this to you. And what I'm going to show you is that it's because of low statistical power in these published studies that we see this characteristic oscillation around 0. Okay? So what's going on here? So what I'm going to do is I'm going to demonstrate this oscillation to you using simulated data. On the x-axis, I have 50 simulated studies. And I'm going to sort the mean effect from each of these simulated studies along the x-axis. And what I'm going to do is whenever the effect comes out significant, I'm going to mark it with a triangle. And whenever the effect comes out non-significant, I'm going to mark it with a circle. Okay? So this is a situation I'm simulating where statistical power is 10%. What that means is that if you were to run a study with this sample size and the true effect was, let's say, 20 milliseconds and the standard deviation of the effect was 150, in only 10% of the experiment, you would have only a 10% chance to detect the effect if it was actually there. Okay, so that is a very bad situation to be in. But let's see what happens if we run an experiment with 10% power. Okay, so I'm going to simulate 50 simulations now. So what you're seeing here is that in the 50 simulations, there were 4 significant effects. Everything else came out non-significant. That's the black circles. And what's interesting to notice here is that the significant effects that turned up, they either had the wrong sign. So this is a negative sign here. The true effect is 20 milliseconds. It has a positive sign. That's that horizontal line there, right? So either this significant effect has the wrong sign, or even if it has the correct sign, the effect is hugely overestimated. Right? So what happens when you have low statistical power is that you will either get the wrong sign if you get a significant effect, or you will get a hugely exaggerated estimate of the effect whenever you get a significant effect. So what that really means is that with a low power study, you are screwed either way. If you run a low power study, you will get a lot of null results, which will be inconclusive. Those are those circles there. If you get a significant effect, you will get a misestimate. It will either have the wrong sign or it will be an exaggerated estimate. And so my guess right now is that a lot of the data that we were working with comes from these low power studies, and that's why we see this characteristic oscillation around 0. Right? So just to show you what happens when power is not low, when we are in a very good situation of having 80% power. So we have an 80% probability of detecting the effect if it's actually there. If I now run the experiment repeatedly and mark the significant effects with a triangle and non-significant with a circle, you'll see what happens now. Right? So what's happening now is that we get very few null results. And whenever we do get a significant effect, it's pretty close to the true value. That's this horizontal line here, right? So it's only when statistical power is high that we will be able to get accurate estimates of the effect, right? And that's not what we have in the literature right now. And so in the 2017 meta-analysis that we published in JML sometime back, we carried out a meta-analysis. We carried out a power analysis using about 100 studies as our for estimating the true effect out there. So these numbers that you're seeing here are an estimated range of effects in facilitatory interference. And what I'm showing you here is the power curves for 20 participants and 40 participants for a range of standard deviations, right, going from 100 to 300. So this is a typical range of standard deviations in reading studies. And what we notice here is that even if we have 40 subjects, the best we can do if the effect is very large and the standard deviation is very low, we will at best have about 60% power. Right? And if you go and read the literature in cognition and the Journal of Memory and Language, you will often find experiments with 20 subjects. The classic paper by Fraser and Rayner, 1982, had 16 subjects, right? And even today in 2020, you will see papers coming out with 20, 30 subjects at most, right, in top journals. So for this class of phenomenon that I'm talking about, interference effects, if the effects are as small as these, then the published studies that we have out there, about 100 of them, they have no chance of actually detecting the effect accurately because the sample sizes are too small. And so just to demonstrate to you that I'm not just talking about theoretical issues in statistics, this stuff happens in real life. I'm showing you a real problem of an overestimation from a low sample versus high sample studies. So this was a Journal of Memory and Language study with sample size 40. Here is the estimate of that race process effect, the agreement attraction effect that I showed you earlier with 40 subjects. And here is the replication attempt that we did with 181 subjects. So what you can see is that the estimate is overestimated. When we increase the sample size, we get a much smaller estimate, right? And if you look at the theoretical predictions from the Lewis-Vasish model, so these are the default predictions from the model with no parametric variation, we are pretty much in the ballpark, right? From when we look at a high sample data set, right? So, so the point I'm trying to make here is that it's fairly difficult. I would say it's impossible to evaluate the predictions of the Lewis-Vasish model or indeed any other model right now because the data that we are working with is mostly coming from low sample studies. Now, all the data is not coming from low sample studies. There are certain experiments that look at really large effects. The classical garden path effects that was studied in the 70s by Lynn Fraser and others, those don't even need an experiment, right? So you can just read the sentence and you know that sentence has garden past you, like the horse raced past the barn fell or something like that. So you feel the hit, you don't need to do the experiment there even. But for subtle manipulations like these fan effect studies and the race process studies, you're going to have to commit to spending a lot more time collecting data if you want an accurate estimate. And without such accurate estimates, it's very difficult to actually evaluate the predictions of the model. Okay, so for me, this was a little bit of a shock, and the question for me was, what can I do to now change the situation? So I'm now spending time running larger sample studies, and I'm trying to replicate my studies to make sure that these studies hold up. And one problem in our field in psycholinguistics is that we tend to report successes, but we don't report the failures. And the part of the reason is that journals don't let you publish failures to replicate or null results or something. So we only see the good news results, which could be accidental type M errors. And that may be the reason why we are unable to replicate many of the experiments when we try to replicate them. Right. So that was the background for the second part of my talk. But I can see that I'm already in my 40th minute of my talk now, so I may be running out of time. So the strategy that I'm laying out right now of running larger sample studies is a very expensive strategy. It takes time and it takes money to do this kind of thing. And so I just wanted to demonstrate to you that in principle, this can be done. It's not an impossible goal, right? So I'm going to show you a little case study to demonstrate how we try to evaluate the predictions of the Lewis and Vasist model using a high precision experiment with a large sample. So again, I'm going to now go back to the fan effect that I introduced at the beginning. I'm going to look for evidence for the fan effect. And the way we did this was by manipulating a sentence in German. So I'm going to show you the sentence first, sorry. Yeah, so here was the experiment that we set up to induce a fan effect in German. So what you have here is a singular nominative marked noun phrase, the subject of the sentence, philanthropist, and you've got a verb, had greeted. And the verb has singular marking as well. So the subject of this verb is going to have to be singular. Okay, so this dependency has to be created. So what we did was that we introduced two distractor nouns inside the relative clause that intervenes between the subject and the verb. So this is the relative clause between the two elements. And this relative clause contains two singular nouns. Here's one and here's the other one, right? So we've got a standard fan effect situation here because we are looking for a singular noun that's a subject, but there are three candidate singular nouns that you have just read. So you should experience more difficulty in processing this verb compared to some baseline condition where the distractor nouns are plural marked. Okay, so that's what we've got in the second sentence here. These are plural marked nouns. Okay, so just to show this to you schematically, we've got a singular subject. The verb is looking for a singular subject, and in the interference condition, in the fan effect condition, we've got two nouns that are not subjects, but they are singular marked. And the baseline condition has plural marked nouns here. Okay. So the empirical result that we got with 180 subjects, this was self-paced reading, was that we see the expected fan effect, inhibitory interference effect that theory predicts. The effect is quite small with a mean of 9 and a confidence interval of 0 to 19 milliseconds. So this is a tiny effect, but it's a pretty precise estimate that we got. And it is as theory predicts. Okay? So what we were interested in doing now was to evaluate the predictions of the Lewis-Vasist model against this observed data. But we wanted to go a little further than that. What we wanted to do was we also wanted to compare the predictions of a competing model of retrieval processes that we could pit against the Lewis-Vasist model. And it turns out that there is such a model out there. And this model is the Bryan-McElree model called the direct access model. So this model is slightly different from the ACT-R model in the sense that it assumes that whenever the system tries to retrieve, the parser tries to retrieve a noun with certain features like subject and animate, one of two things can happen. The first thing that can happen is that you access the subject correctly. So that would be a correct retrieval, and that would take beta milliseconds. The other possibility is that you fail to retrieve the correct subject, that is resident. You make an incorrect retrieval of the distractor noun, and that also costs the same amount of time as the correct retrieval. So this is an interesting feature of Bryan-McElree's model, that whether you retrieve the correct thing or the wrong thing, the amount of time it takes to complete that retrieval is going to be the same. It's constant time. Okay? This is different from the Lewis-Vasist model predictions. Okay? So in the McElree direct access model, you will either retrieve the correct thing or you will retrieve the distractor. If you retrieve the distractor, you make the incorrect retrieval, you will make an attempt to re-retrieve the subject. So that's what we call a reanalysis here, right? And that reanalysis will cost you some extra time, let's say delta milliseconds. Yeah? And so it's possible that you succeed in retrieving the subject in the reanalysis step, or you fail entirely and you don't retrieve anything at all. So this model is very different from the ACT-R model. If you remember, in the ACT-R model, the cause for the slowdown at the verb is the fan effect here, right? This Q overloading that you have of the animacy feature matching two nouns. In the macillary model, it's the result of a two-step process. You will occasionally fail and then spend more time trying to retrieve the subject. Now, this process can be characterized as a finite mixture process. So you can think of the observed reading times that you see as probabilistically coming from one distribution, the success distribution, where you immediately retrieve the item successfully with some probability P, or you initially fail and then you spend some extra time, delta milliseconds, trying to retrieve the subject a second time. Okay, so this is the reanalysis step, and this would be with probability 1 minus p. So this basically describes a finite mixture process now. And so one of my students, Bruno Niesenbaum, he noticed that the direct access model, which had never been implemented computationally, he noticed that this model could be implemented as a finite mixture model. So he implemented it, and he compared the predictions of the Lewis-Vasich models with that of the direct access model using the data set that I just showed you, right? So this slowdown that we observed in the fan effect, okay? So that is the way that we are trying to evaluate the predictions of the Lewis-Vasich model by setting up a competing model and having high precision data to make sure that we have precise estimates, or accurate estimates at least, of the fan effect that we are looking at. What we are trying to figure out is what is the underlying cause of this fan effect? Is it the fan effect as assumed in the ACT-R model, or is it the result of the mixture process assumed in the direct access model? Okay. So now I'm going to show you the results of this model comparison. Right. So what I'm showing you in this slide is the predictions of the ACT-R model, of the Lewis-Vasich model, the predicted reading times as violin plots. So what these little things that you're seeing here, these are called violin plots, and they are the predicted distributions of reading times from the model when the model correctly retrieves the subject, or when the model incorrectly retrieves one or the other distractor nouns. So this was the first distractor noun, the second distractor noun, and the last block here shows you the predicted reading times when the system completely fails to carry out a retrieval, right? So one thing I didn't mention yet was that in the experiment that we did, after each trial, we asked the subjects who did the action, who did the greeting. And so they had to say whether it was the first noun, the second noun, the third noun. So they had to name the noun. They had to actually write it down. Or they had to say, I don't know. Okay, so that's how we got responses from each subject. And we have the reading times and the responses from each subject for each of the four possibilities. And so what you see here is that the model, the Lewis-Vasich model, actually predicts the correct retrieval times more or less accurately. These are the quantiles on the x-axis. It predicts the observed data more or less accurately. The observed data is the x's that you're seeing, right? It misses the observed data a little bit towards the edge of this distribution, but for the most part, it's doing okay. But the Lewis-Vasich model doesn't do so well with the cases, with the trials where the response was incorrect. So the model is predicting slower reading times than were actually observed. Right, so you can see that the x's don't land inside the violin plots. So this is not a very good performance of the Lewis-Vasich model, but of course, very good is a relative term, right? So let's see what happens with the direct access model. It turns out that the direct access model, which is the mixture model, also predicts, we can also generate the predicted reading times from this model as a result of this mixture process, having estimated all these parameters, right, in the model. And what we find is that the direct access model does a spectacular job of predicting the observed distributions of reading times in the correct target cases and also in the incorrect cases. So actually the direct access model outperformed the Lewis-Vassich model in this particular data set. Now, we were very interested in finding out why the ACTAR model actually fails to capture these observed reading times when the retrieval was incorrect. And so one possibility was that the standard deviation of the retrieval time when the correct item is retrieved and the standard deviation of the retrieval time when the incorrect item is retrieved, that could be different in principle. In the ACTAR model, those standard deviations are identical. And that's why, because the same standard deviation applies in all these three boxes, that's why the model is not able to, is overestimating the reading time here. So what we did was, we changed the assumption in the ACTAR model that the incorrect retrieval's distribution of finishing times has the same standard deviation as the distribution of correct retrieval time. So the green distribution that you're seeing is showing you the distribution of finishing times when you retrieve the correct element. And this other color, I'm actually colorblind, so I can't actually say what color this is. But this other color is showing you the distribution of finishing times for the incorrect retrievals. So we changed the standard deviations for the retrieval of the target and the competitor in the ACTAR model. And then what we find is that indeed the ACTAR model is able to get a better fit to the incorrect responses here. So the upshot of this story is that in this model comparison for this one particular data set, what we found is that the direct access model outperforms the default Lewis-Vassich model, the activation model that we had set up with the default parameters. And we also found that the direct access model and the two variants version of the Lewis-Vassich model are equally good for explaining the data. So right now what we are doing is we have now expanded the benchmark data sets that we are going to use to compare these two models, and we are working with a range of other data to carry out the same model comparison to see what the relative performance of these two models is. So one early result that we have right now is that the default Lewis-Vassich model actually outperforms the direct access model on data from a phasic individual. So we've got self-paced listening data from David Kaplan, where we find better performance of the Lewis-Vassich model than the direct access model. But the jury is still out on this. It'll take us a few years to finish a range of benchmark tests to find out which model can better explain the distribution of finishing times in observed data. And of course, as I mentioned, the biggest problem that I'm facing right now is that I don't have precise estimates of the interesting effects. So we have to create the data ourselves to estimate these effects. And that's, of course, taking a lot of time. I have several PhD students working on this right now, trying to collect large sample data sets. So I'm almost at the end of my talk now, so I'll just quickly tell you about what I'm working on these days. So one of the things that has been bothering me for the last 3-4 years is that we have spent our entire lives in psycholinguistics studying average effects. So when we talk about the fan effect, we have, let's say, 180 subjects. We just take the aggregate of that and we want an estimate of the overall effect. But statisticians for a long time have been pointing out that modeling the average actually is modeling an abstraction. It's the variability around that average that actually carries a lot of information. So there's Spiegelhalter is a very famous Bayesian statistician in Cambridge, and he's a medical researcher as well. So he talks about, individual level effects in the medical context, which become very critical if you're thinking about situations like, cancer diagnosis and so on. You don't really care what the average survival rate is. You care what the average survival rate is for you, as an individual. So the individual is very important in those situations. And I think that we have missed the boat in that respect by modeling only average effects. And so an example of what we do and what we should be doing is shown here. So what I'm showing you here is the individual level estimates from one published study of a facilitatory interference effect that I discussed earlier, the race process effect. What you're seeing is 40 subjects estimates from a linear mixed model. These are shrunken estimates for each of the subjects. And what is interesting to notice here is that the subjects all show negative effects, but the magnitude of the effect varies quite a lot. Now, the interesting thing is that what we study in psycholinguistics is the average of all these effects. That's this observed effect here. And so the model can handle that. Our model, the Lewis-Vasich model, can explain this effect very nicely. No problems. But I think that there are interesting reasons why subjects might show this range of variation between subjects. Okay? So that's what I'm studying right now, both empirically and using the Lewis-Vasich model. So one interesting thing in the Lewis-Vasich model is that the different cues that you have for doing a retrieval, for example, if I'm looking for a subject and an animate noun, the cues need not have the same weighting. Right? And so one interesting property, one prediction of the Lewis-Vasich model is that if you make the syntactic cue much stronger, if you increase the weighting of the syntactic cue more, then the interference effect shrinks. Right? If you give equal cue weighting to both subject and animacy, then the interference effect is much larger. Okay? So the implication of that is that these small effects that you might be seeing, they could be for people, these could be representing people who have a different cue weighting for the syntactic cues than the subjects who are showing larger effects. So these subjects might be engaging in more superficial processing, and these subjects might be using the grammar more accurately to access the element in memory. So one easy way to test this is to take L1 and L2 speakers. So L1 speakers will be fluent in the language, and they will have very strong cue weighting, and they will show small effects of the interference effect. But L2 speakers will not have the same syntactic representation that native speakers will have, and they might show bigger effects. So we'll be running some experiments with bilingual populations to investigate this in the future, and this might be an interesting way to get at why these individual level variations are happening. By the way, this is not something anybody ever discusses in the literature. We only model the average effect, and I think we are missing some important details about the models that we are looking at by ignoring these individual level effects. So that's one direction that I'm going in next. And so this is basically close to my last slide now. So the other things that I mentioned that we are doing is we are now systematically investigating the Lewis-Vasich model and the direct access model on a very large set of data from individuals with aphasia. This is English data, but we're also creating a large database in German, and we'll be carrying out that evaluation this year. Another thing that we are doing is that we are trying to build a more sophisticated version of the Lewis-Vasich model by having a more principled way to talk about the features that you have that are used for retrieval. So right now we have a very primitive way of thinking about the retrieval cues, right? So we say things like, oh, the retrieval cue is subject and animacy, or subject and singular, right? These are discrete features. But what you can do is you can look up a large corpus of English or German, and you can derive vector representations of each of the words. And you can, by taking the angle between the vectors, you can figure out the similarities between the nouns in memory, right? And you can use that to build a model that actually takes, in a data-driven way, it has a more principled way to derive lexical features which can be used for retrieval cues. So we have a paper under review that does the first line of work in this direction. And of course, because of all this type M error problem that I have been talking about today, I'm very obsessed with running larger sample replication attempts to reproduce all the key claims that have been made to make sure that I have accurate estimates before I start doing the hard work of model comparison and model evaluation. So basically, for the last 20 years, I've been trying to do this, but now I realize that I can't do it, and I'm going to now start doing this. Right? And another thing that we have started now in collaboration with two US researchers, Tal Linson and Brian Dillon. Tal Linson is in Johns Hopkins and Brian Dillon is in UMass. We are now working together to develop a systematic set of benchmark data, large sample eye tracking data for English and German that covers all the major phenomena like garden pathing effects, interference effects, and other things that are of interest for the field, so that when you develop a new model, and you want to evaluate that model's performance against the existing models, for example, the Lewis-Vassich model, you have a benchmark over which you can outperform the baseline model. So basically, I just want to scale up the toy model comparison I showed you today to a much larger set of benchmark comparisons. So I think that this will be a much better way to develop theories in the field, because right now what's happening is that people keep publishing papers building newer and newer models of sentence processing. But typically what they will do is that the entire model is all about subject and object relatives in English. That's it. They will not look at anything else, right? So you will see several models that can only explain that one thing, right? And what we need is a range of benchmark phenomena that the model has to show good performance on. And so this idea is actually not new. So this idea is pretty standard in cognitive psychology. I think, for example, in eye movement research, if you look at the work happening in the easy reader model evaluations and other models that are used for studying eye movement control, they have a set of benchmark phenomena that they have to be able to explain before they can, sit at the top table as a real model, right? So that kind of benchmark we don't have in psycholinguistics, and I think that is important to develop, and so I'm working with several people to do this. Okay, so I just want to close by thanking all my lab members. These are most of the people that have been with me. Many of them are professors now, and the person in the center is my lab manager. She's the most important person in our lab. Her name is Hanatika, and she makes everything possible for us. The funding came from the German Research Foundation and the University of Potsdam and a large collaborative research center that we have in Potsdam. So that's where all the research money comes from, and that makes it possible for me to run these large sample studies. Thank you.
Can you hear? Can you hear me? Can you hear Julie?
Yes, I can hear you. Yes. Oh, is Judy there?
Yeah, hi. So I was wondering about that comprehension question that asked about exactly the phenomena that you were interested in, and I wonder if you think that, how that impacts your results.
Yeah, so the comprehension questions, basically, so what's happening is that the subject is asked to decide who did the greeting, for example, right? So how does that impact the processing? Well, one thing that it does do is that it forces the subject to pay attention to what's happening in the sentence. You know that when we run these experiments, people tend to zone out, right? They stop paying attention to the sentences. So they are forced to pay attention. That's one thing that happens. Another thing that happens is that it, of course, attracts the the participants' attention to the fact that they will be asked, who did what. And so this might, of course, influence their behavior. So there's actually another problem with this experiment, which is that we are assuming that the subject's response as to who did the action, the greeting action, is actually telling us about what the retrieval was that happened earlier. That is a very big leap, and it probably is not a very valid assumption that the question response tells us about what happened a few seconds earlier during the retrieval process. But that was the best we could do in this particular experiment. I think that in the future, I will probably put the subjects under time pressure to try to get a fast response from them, to get a more accurate estimate of what they had actually retrieved. Did I answer your question, Julie?
Yes, thank you.
Okay. Yes.
Hi.
Go ahead. Yes. Yeah.
So one of the most reliable effects is the surprise effect. So in this manipulation, actually, you manipulated condition matching, but also the conditional probabilities of the verb after the previous prefix will be slightly different. So, but the actor actually doesn't consider that factor, right?
Are you talking about surprisal here?
Yeah. So the question is actually the conditional probability of the verb,
Yes.
given all the prefix in those two sentences, are
Yes.
different. So that
How do you know that? Sorry, hang on. So how do you know that? So the sentence has a very minimal manipulation. It has singular versus plural distractors, but everything else is the same here. So the syntactic. Yeah.
I'm not saying the surprisal values will be different, but I'm just asking whether you actually checked those values. So whether you controlled those values.
No, we didn't. And the reason we don't do that is that we are assuming that the syntactic structure being identical will not change the conditional probabilities of the upcoming predicted verb. You see? So, I mean, your confidence in surprisal is, I think, is very optimistic actually, because I have attempted to replicate the key results on surprisal, and I have failed every single time. So some of the key claims about surprisal, for example, the Levy and Keller 2013 experiment, I ran 7 replication attempts of that, and I failed every single time to replicate those. So the jury is out on surprisal as far as I'm concerned. So I wouldn't be so sure about surprisal having a dramatic impact in this case, because even in the cases where it's supposed to have a dramatic impact, I don't see the evidence there.
Thank you.
Yeah. Yes, Rick.
So one way to address the statistical power problem is to run larger studies as you're doing, which is amazing.
Yes.
But another approach is to try to get more data out of each experiment. And so, for example, instead of having predictions about just critical regions, as in the surprisal experiments that are kind of corpus-based, why not move toward having the model make predictions on every single word, which in principle it can, the models that are general enough, and then increase the number of data points by a factor of, well, average length of sentence per experiment.
Yeah. You could do this for some of the models. For example, the Lewis-Wasish model, yes, you could do that for the target sentences of interest. But many of the competing models, for example, the direct access model does not have any parser associated with it. So it would be difficult to build comparable predictions for that model unless one embeds it inside some kind of parsing story. That certainly is possible, yes. The reason we don't do that is that the theoretical predictions that we were interested in were really the events that start at this target word. And so if we try to now take into account every single word in the sentence, we will certainly have more data, but we won't have precise estimates for the target events of interest. So that's why I'm focusing so much on the target word and trying to get more precise estimates of those first. But eventually, if we can have scaled up models that can give us detailed word by word predictions, sure, that would be a great way to proceed.
So I got one last question. In
Yes.
the 7 failed attempts to replicate the surprisal studies,
Yes.
how many
Yes.
were they high power experiments?
Yeah. So let me see if I can show you what that's all about. So just give me 1 second. I'm gonna have to find my paper. Here's the one, right? So can you see this paper? Maybe not.
Not now.
You may have to
No, hang on.
restart.
I will just do that. Sorry. Yes. Um, I want to share, yeah, this is what I want to share. Can you see this?
Yes.
You should be able to see this now, right? Yeah. Okay. So this is the paper that came out in 2018, and we tried to replicate the Levy and Keller 2013 effects, and there were 7 experiments. The first 6 experiments had the same sample size as Levy and Keller. So this was a surprisal manipulation. What they had was that there was a verb, and they were manipulating the predictability of the verb as a function of the number of interveners that appear between the subject and the verb. So, for example, in this last sentence, you've got an adjunct and a dative that sharpens the expectation for the verb. So you should see faster reading time here than some baseline condition here, for example. Okay? So they had 28 subjects in each of their studies, right? And so what I did was, so here's what you have, okay? So there's the first experiment here. This is the significant effect in the first experiment. These are my replications with the same sample size as the Levy and Keller experiment, so 28 subjects, okay? So I'm unable to read. So this is the type M error situation again that I just tried to show you earlier. And in the second experiment that they carried out, they got a significant interaction for their factors, and these also I failed to replicate with the same sample sizes that they had. So these were basically the first 6 experiments were like this, and then what I did was I ran a pre-registered 100 sample study, and that's this one here. Okay, so what you see here is that this was a claimed interaction in the original experiment with 28 subjects, right? So they were claiming that there was an interaction between experiments 1 and 2. And so what I did was I carried out a 100 sample replication attempt of that claimed interaction. And that's the estimate that I'm getting there, bang on 0, right? So this is what I mean when I say that the key claims of this of the Levy and Keller study don't really pan out when you run a high sample study. I must say, though, that the Linson and Jaeger experiment in 2016, I still believe that they found strong evidence for surprisal there. That was a solid result. But that's the only solid result I'm aware of on surprisal. And that's pretty surprising to me, you know. I would have expected more clear evidence there. Rick, did I answer your question? Is that okay?
Yeah, definitely. Thanks.
Hello. Thank you. A great talk.
Yep.
Extremely clear. So thank you for bringing all of us along. The question that I have is more practical. So
yes.
I think you are trying to tell us, I mean, the message that is loud and clear is that we need those high-powered studies. In terms of feasibility, I'm looking at our, PhD student and the time that it took you to come up, to finalize the 180, participants study.
Yes.
Which
yes.
I agree,
yes.
brings a lot of validity to the results. But how
yes.
can we, actually allow the field of psycholinguistics to keep thriving by allowing students to lead those experiments with
yes.
a more feasible, way of doing things, so that they can get results by the time they finish their PhD.
Sure. Yeah, that is a very important question. So you're right that I'm in a very lucky position. I have a lot of money right now, and so I can do whatever I want, and I have the time as well. But my students don't have that luxury, and so my solution to that problem is that if you're a student and you have 2 years to run your experiments and you can only run so many subjects, then do what you can, because eventually you can put together the evidence that exists on that topic to derive meta-analysis estimates, right? So eventually there will be enough information. Each of these studies that you're seeing here is underpowered, each of these 10 studies, but each of them appeared in the Journal of Memory and Language. And that's okay, because there's still information. There is still information in these studies. The information is not there in these studies themselves, but if you put together the information over time, you will find at least some estimate of the information. The problem there is that we tend to hide the failed experiments, And so what happens is that only the big results show up, and that skews the meta-analysis estimates. So it would be nice if students were to just openly publish whatever happens. If they mess up, they don't mess up the experiment. If the experiment doesn't show clear results, that should still appear somewhere. And that is still an achievement, and that's still information that will be useful when we're trying to derive the meta-analysis estimates. So, what happens to me is that some of my subjects, they work with aphasic patients. They can only get 7 patients for their entire PhD. That's it. There is no opportunity to get 40 or 50 or 60 patients. So that's perfectly fine. They do what they can. What I do with them is that I do Bayesian analysis with them. So the Bayesian data analysis methodology is designed for situations where you have less data, but you have a lot of prior knowledge. So you can bring the prior knowledge into the analysis through the prior distributions. So when you have sparse data, you can change your data analysis methodology to take prior knowledge into account, and you can use this sparse data in future studies to incrementally build up your understanding of the phenomenon, just like I've done over here, right? This meta-analysis.
I have a follow-up question. In this talk, you seem to take the null hypothesis or the zero effect is meaningful. But the question is actually whether the null hypothesis is worth discussing. So why not just taking the parametric estimation approach rather than taking the credible interval includes 0 or not?
I don't take the credible interval as my criterion at all. So the way I do my modeling is very different than the standard null hypothesis testing. I don't do any null hypothesis testing. So let me just show you how I would.
0 is actually included or not.
No, I never said that. Did I ever say that in today's talk?
I'm sorry, yeah, I misunderstood.
Yes. Maybe I implied that, and maybe you inferred that, but and maybe just for communication purposes, I was talking about whether 0 is in it or not. So let me just get to something I want to show you. Here. This is how I do my model evaluation, right? So this is the region of practical equivalence method. Can you see this? Yes. So let's say my model prediction is this region, or maybe my theory predicts this range of effects. So what I'm going to do is I'm going to run my experiment until I achieve a precision. That means a 95% confidence interval of width 40 milliseconds, okay? And so there are 5 possible outcomes that I can get. I can either land inside my predicted range, or I'm going to overlap with the predicted range, or I land outside entirely, right? That's how I would do my inference when trying to evaluate whether my model's predictions are validated or not. So what typically happens to me is that my model predicts, let's say, this range of effects. I get an overlap with the data, but I very rarely get an exact landing inside the predicted range, So for me, null hypothesis testing is not the important thing to do. In my talk, I may have used the confidence intervals to indicate, that 0 is included or not. That was just because that's how other people talk about these results. So in order to be able to communicate with them, I bring up this fact that 0 is there or not. But in the actual model evaluation, that's not how I do my work.
So do you personally recommend the rope method to talk about whether?
Yes. So whenever we pre-register our analyses before we run the experiment, we timestamp our predictions, So we set up the region of practical equivalence in advance, and we use the region of practical equivalence as our stopping rule, right? So we keep running the experiment till we reach that precision, and that's when we stop running subjects. That way we don't waste subjects, when we're running the experiment. And then we know whether we landed in the predicted range or not. So I have a 2020 paper in the Journal of Memory and Language that does exactly this. We use exactly this approach.
But isn't the definition of the rope region rather subjective? Because you need to choose how wide.
Yes, it is not subjective because the rope is decided based on prior data, based on meta-analyses or based on the model predictions. Right? So in that sense, it's not subjective. In another sense, everything is subjective. So even when you fit a frequentist model, you decide on the normal likelihood. Why did you decide that? That is a subjective decision. We just don't realize it because the software hides that from us, you know?
Thank you.
Let's thank Shravan.
Thank you.
Thank you.
Thanks. It's getting late there.
Thanks. No, it's fine.